Okay, yes, so I'm very happy to be here to talk about my recent work. And first, I would like to thank the organizers for providing this amazing chance. And in this talk, I will discuss particle production from oscillating condensates. Wait. Condensates. And this talk is based on a recent work with Ziliang Wang and an earlier work with Marco Druce, Jason Gravan, and Yang Haiyan. And this is outline of this talk. First, I will give a brief introduction and talk about some motivations, and then I will briefly review particle production from oscillating condensates in simple methods, and I will move forward to a description of particle production in non-equivalent quantum field theory. At last, I will give conclusions and outlook. So here, everybody is familiar with particle production, and particle production is perhaps the most important phenomenon in nature. Two prominent applications are Hawking radiation and reheating. Okay, it is related to two deepest questions in theoretical physics. In Hawking radiation, it is about information. So where does the information contained in the black hole go after the evaporation of the black hole? And for reheating, it is about matter. So where does the matter in our universe come from? And so in Hawking radiation, particle production, so in Hawking radiation particle production, the source for particle production is a curved space-time, and in reheating, the source for particle production is usually a scalar background. And this is the reheating. This part is the focus of this talk. And in cosmology, there are many scalar backgrounds. They can be classified by symmetry. So in the first class are constant backgrounds. For example, the dark energy or Higgs wave. In the second class are the time-dependent, but especially homogeneous backgrounds like inflaton. And in recent years, people are also interested in time-dependent and also especially in homogeneous backgrounds like boson stars. And we will focus on the second class. In particular, we will focus on reheating. And this is the picture used by Thomas in previous talks. And this is a general picture for inflation and reheating. And usually we assume a scale with such a potential. In this region, the potential is nearly flat. And if the field is located at this point, it will slowly rolls down and induces inflation. And when it rolls to this point, the field would start oscillating about its minimum. Then the reheating begins. There are usually two steps for reheating. If the amplitude of the oscillations is large, then particle production from the oscillating condensate is non-perturbative, and usually this is called preheating. So when the amplitude becomes smaller and the particle production becomes perturbative, and it is perturbative reheating, usually a particle production from preheating is much more efficient than from perturbative reheating. So a question is that why do people care about perturbative reheating? The answer is that it determines whether or not reheating is complete, and also it is also possible that in some inflation models, preheating is inefficient or absent. So in this case, perturbative reheating is also very important. So we will later we will talk about perturbative reheating. It means particle production from oscillating scalar condensates near the minimum of the potential. Now let me recap how to describe particle production from an oscillating scalar background. So suppose we consider an interaction between two scalar fields, phi and chi. Okay, and suppose the background, suppose the field phi has a non-vanishing one-point function, to distinguish, I will call the 1-point function of phi as var-phi. Okay, so in this talk, so I call this var-phi, and this 1-point function, this background field, would induce a time-dependent mass term for the field chi. Okay, this is a mass term for the chi field, and it has a time-independent part, and usually this is time-dependent. If the time-dependent mass term is larger than the time-independent mass term, then particle production is non-perturbative. And in this region, actually the particle states of chi are not well defined because the mass term is time-dependent. But still, one can study particle production by applying the Floquet theory in analyzing the equations of motion for the mode functions of chi field. And usually the equation of motion for the mode functions takes the form of Mathieu equation or Lam equation. This method is also very similar to the Bogoliubov transformation, usually studied in gravitational particle production. So then if the time-dependent mass term is much smaller than the time-independent mass term, then the particle production is perturbative. And actually this naive method is to add a friction term to the equation of motion for the background field of var-phi. And here gamma is taken to be the one particle decay rate of phi field. There are actually many problems with this method. So the first question is this justified? And also, if the particle production happens at finite temperature, then how to include some effects in this method? And also, because gamma is computed in vacuum, it is not sensitive to the evolution of the background field. Then how to include the backreaction effects? In particular, if there's a Z2 symmetry for the phi field, as for example in this interaction, then the one particle state for phi is stable. It means that gamma is 0. However, the condensate still decays. So this method cannot capture. It's not it's not complete. And also with this equation of motion, the decay of the condensate always takes an exponential law. But as we will see later, this is not true. The decay of the condensate, the oscillation, will take a very complicated form. Now, now actually there's an improvement for this method, but for time reason, I will not discuss it in this talk. Now below, we will talk about particle production from oscillating scalar condensates in non-equivalent quantum field theory. So this is our model. And this model is also very similar to the one used by Thomas, although we consider self-interactions or other interactions. It's not just linear. And but the potential is chosen to have Z2 symmetry. This model is very popular in phenomenological studies. So if you take phi to be the inflaton and chi to be the Higgs, then it is the Higgs-Porter inflation. And if you take phi to be the Higgs and chi to be the dark matter, then this is one of the Higgs-Porter dark matter models. You can also take phi to be the inflaton and chi to be the dark matter, and sometimes it is called inflaton dark matter. Okay. Now, since the field phi has a non-vanishing one-point function, you have to expand phi about this one-point function, the background, the var-phi, and the phi is this phi, the zero phi is the fluctuation field. Okay. So the total action can be written as a sum of this one. This is the action for the background field, or this is the classic action, and this is the action for the fluctuation fields. So so this action actually describe. So particles are usually defined as excitations for the fluctuation fields, phi and chi. This is the background, and now as we said that we consider perturbative particle production. This means that this mass term time-dependent mass turn is smaller than the time-independent mass turn, and we will take the mass turn as a vertex. So they are on equal footing with other interacting terms. And then to derive the equation motion for the background field, we will use the effect action. And the truncated effect action is given as following. Here, this is the class part, and we have phi plus and phi minus because we are using the closed time path formalism for the non-equivalent KFT. I left some slides in the backup, but here I will just skip this. And a solid line here, a solid line is denotes the propagator of the field phi, and the dashed line denotes the field of the chi field, and a V cross denotes the background field. So these two diagrams, is local, and they give rise to the mass corrections. In the second line is self energy, and in the first line is four-vertex functions. They are important to induce dissipation of the background field evolution. From this effect action, you can derive the equation motion. You see, this is still the classical part, the classical equation motion from this part. And here we have absorbed the mass corrections from this two diagram into the capital M phi. Okay. And this self energy and the four vertex will give us two additional terms. This is from the self energy and this is from the four vertex. In principle, these two terms are non-local. They are non-Markovian and have a memory effects. In our paper, we solve this equation motion perturbatively, but in this talk, I will not discuss the details on how to solve this equation motion, and I will simply present our solutions. The solutions takes the general form. Here, A of t is the envelope function of the oscillation, and as we will see, the frequency, because we consider the particle production near the minima. So in the classical, at the classical level, it is oscillating with frequency m phi. However, with these terms, and the frequency will have a time-dependent correction. All these functions, A of t and f of t, depend on several microscopic quantities. They are the self energy of four-vertex functions evaluated at certain frequencies. A tilde means that these are the Fourier transform of the self energy of four-vertex function. So basically, you already consider some real part and imagined part of the self energy, or real part and imagined part of the four-vertex function. Okay, two very important quantities are the imagined part of the self energy, gamma. This is come from the imagined part of this diagram, self energy, and the imagined part of the four-vertex function, coming from this two diagram. Okay, and before we show you the solutions, I will first discuss the physical meanings of gamma and sigma. From the conventional QFT at 0 temperature, we know that the imagined part of a diagram. So in this diagram, the initial states are the same as the final states. And the imagined part of this diagram gives you the decay probability from the initial two particles to the particles in the loop. Okay, you simply color this diagram, and then you can interpret the imagined part as the decay probability of this process. But when you cut this diagram, you have to make the particles in the loop on shear. So this process must satisfy the on-shear conditions. At finite temperature, the cutting rules are more complicated. So this is because at finite temperature, you have a plasma, and actually it is possible to put the particle in the loop to the left. For example, in this case, you can put one particle phi to the left, and then this diagram, the imagined part of the self energy can describe a decay channel like a Wi-Fi. Wi-Fi is the background, the real clock Wi-Fi, and also a phi in the initial state. And this in total decay to 2 phi particles. This is a decay for the Wi-Fi, right? Because a quantum in the condensate disappear. And in this case, you can also put one chi particle to the left, and then this describe a decay for the Wi-Fi as a process like this. And here you can also put the phi to the left. So the reason that you can put some particles in the loop to the left because we have a plasma, and in the plasma, the condensate, it's possible for the condensate to find a particle in the plasma and analyze together into normal particles. Okay, all these processes are called Landau damping. I mean, so you can also imagine some other processes. For example, you put 2 particles to the left, but all other processes cannot be made on shell. So you can only have these 3 decay channels. They are called Landau damping, and they disappear at a 0 temperature, because at a 0 temperature you cannot find the condensate cannot find a particle as the initial state. Okay. For the similarly for the proper four-vertex function, this 2 diagram, the imagined part of the this diagram sigma give a decay channel 2 background field quantum to chi particles. Of course, if you cut this diagram and you describe Wi-Fi to 2 phi, this also can be on shell, but however, you must have the phi particle in the loop having 0 momentum, and this does not contribute to the condensate decay. Okay, so this is the physical meaning of gamma and sigma, and we will see that in the solutions, gamma and sigma will induce the decay of the oscillations. Now, this is the solution for the static universe. As you can see, the gamma, the imagined part of the self energy, induce an exponential decay law. However, the sigma, the imagined part of the proper four-vertex function, induce a power law decay. So the general expression for the envelope function does not take a naive exponential law. It is complicated. In an expanding universe, it is more complicated actually. The decay of the condensate energy density at a large time is described by this equation motion. We have 2 contributions from the gamma and from the sigma. So gamma in flat spacetime or in a static universe, if gamma is 0, the decay of the condensate energy density is still complete, because you can always have a non-vanishing as long as the envelope function is not vanishing, and then you can always decay via the sigma channel. The sigma channel. This is gives the gamma channel. Okay, now this is an example of this equation. If you take gamma to be 0, and you find that the red line gives the energy density of the condensate, and then you find that the decay is complete because the energy of the stored in the condensate is much lower than the energy of the produced particles. However, as we will see, the conclusion is very different in an expanding universe. And this is our solution in a radiation dominated universe. And now the envelope function takes a more complicated form, but I will simply show you some examples, numerical examples. This is the evolution of the scalar condensate. The red line gives the full solution, while the purple line, this is the purple line, gives the damping of the oscillation due to the universe expansion. So if if you can take all the interactions to be 0, then still there's a damping because of the universe expansion. And the brown line is the damping of the oscillation due to particle production. means in an expanding universe, the evolution of the energy density at a larger time is given by this equation. And now we have an additional term, the Hubble term. Now you see that if you take gamma to be 0, so if you take gamma to be 0, means that the gamma channels are absent. And then at a later time, actually the damping, the decay of the energy density will be dominated by the Hubble term, because A of t, because the envelope function becomes smaller and smaller. So this means that the damping of the oscillation will only caused by the universe expansion, not by particle production. And this means that in that case, the decay of the condensate is not complete. This is an example. If gamma is not vanishing, we see that the decay of the energy density is complete. And if the gamma is not vanishing, it means that the gamma decay channels are present. Then the decay, are absent in this case. Then the decay of the condensate energy is never complete. The situation in a matter-dominated universe is similar. Still, we show a similar example. The red line is the first solution, and the purple line and the brown line gives you the damping due to universe expansion and the particle production. In this example, these two lines, the purple line and the brown line, overlap. Again, if you in the case of gamma is non-vanishing, the decay of the energy density is complete. However, if gamma is vanishing, then the decay of the condensate energy is not complete. The transfer of the energy is never complete. Now, let me give some conclusions and outlook. So in this work, we obtained analytical solutions for the evolution of the oscillating scalar condensate in a static, radiation-dominated, and more matter-dominated flat FLRW universe in the small field region. By small field, I actually means that the time-dependent mass term is much smaller than the time-independent mass term. And also, we found that the gamma channels, the channels induced by the self energy, are essential to ensure a complete decay of the inflaton condensate in the Z2 symmetric two-scalar model. And also, the gamma channels are Landau damping. They present only at finite temperature. So if you imagine some inflation models and the reheating starts with the perturbative region at 0 temperature, then this Z2 model cannot be a successful inflation model because the decay of the condensate never complete. And at last, we give an outlook. In this talk, in the numerical examples, we simply take the microscopic quantities as a fixed number, for example, the gamma, sigma, mu, and so on and so forth. And so actually the self energy, a closed expression for the self energy is not known. And we are currently working on it and try to give a more rigorous study on perturbative reheating. At last, a phenomenological study on perturbative production of dark matter from oscillating scalar condensates based on our theoretical results is in progress. Thank you for your attention. Maybe I'll go to.
Okay, thank you for this nice talk. Now it's time for questions. So do you have any question, Gerardo?
Hi, thanks for this very interesting talk. In this model, if one of the scalars that you consider was the Higgs, would that be stable under radiative corrections from the rest of the standard model?
Well, so for the Higgs, in the Higgs instability, the Higgs is unstable in a large scale of the field value. And in this case, we consider real-time evolution, and then the tunneling, I mean the transition effects are can be neglected, I think. And I mean so in under here's talk, the tunneling effect. I mean so even by the Hawking-Morse transition, they are exponentially expressed. So I don't think they will affect the real-time evolution of the reheating process.
Okay, thank you.
Okay, I have a short question because I think I missed something. So can you repeat if you I'm not sure if you said it, the main differences between Minkowski spacetime and expanding universe in your work regarding this dissipation or this damping?
Yeah. So so the main difference is that now you can see that the decay of the condensate energy density at a larger time is given by this equation motion, and this is a flat spacetime or a static universe, and then the damping is given by gamma and sigma. Actually, you can understand this equation from the equation motion. You see, this is our equation motion, and this is actually this is from the self energy, and this will give you a gamma term. A gamma term actually is gamma. So this is a linear term in the background field, and this is a cubic term because you have 1 power Wi-Fi here and 2 powers of Wi-Fi here. This is a cubic term, and this is will give the sigma channels because sigma is the imaginary part of the proper forward function. So in flat spacetime, there's no the Haber friction term, and then the decay of the energy density of the condensed energy density will dominated by gamma and sigma, and they are all from the particle production. I mean, so the decay. Why the energy, the condensed energy density decay? Because they are particle production from gamma channels and sigma channels. So even the gamma channels are not there, we still have the sigma channel, right? So the sigma channel will finally make it possible to fully transfer the energy from the condensate to normal particles. However, in an expanding universe, there's an additional term because we added Haber friction in the equation motion, and now so if gamma is 0, because gamma is not time dependent, so it's if gamma is not 0, then this term will always be the dominant part at later times, right? Because these two terms will decrease, and this term will be dominated, and then so it means that the decay of the energy density will be complete because the gamma channels will always be there and will dominate at later times. However, if gamma is vanishing, then you have two terms for the damping of the oscillation. One is from the universe expansion, and one is from the particle production. But in this case, the contribution from particle production is from the sigma channel, and this contribution will become less and less dominant. It will become subdominant compared to this term because the envelope function becomes smaller and smaller. So it means that finally the decay of the energy density is due to the universe expansion, not particle production.
Okay.
Yeah, and then in this case, it means that if gamma channels are not there, then the decay, the transfer of the energy from the condensate to the particles will not be complete. Yeah.
Okay.